Good morning, everyone. Today I'm presenting my computer vision project on automated receipt information extraction using a hybrid YOLO and OCR approach. The system I developed combines high resolution object detection with optical character recognition to automatically extract three critical pieces of information from receipt images: the vendor name, transaction date, and total amount. This work has practical applications in expense tracking, accounting information, and digital archiving. Anywhere businesses or individuals need to process receipts efficiently. Let's dive into the problem. Let me start by showing you why receipt parsing is so challenging. On the left side, you see three types of receipts we encounter in the real world. The top one has faded link, common with thermal printers that degrade over time. The middle one shows geometric distortion from wrinkled or folded paper, and the bottom one has high contrast shadows from poor lighting when photographed. These visual challenges create three key pain points. First, noise versus signal. Traditional OCR engines passes everything on the receipt, including decorative logos and background text, making it hard to identify the relevant fields we actually care about. Second, complex layouts. Unlike standard forms, receipts have no consistent structure. Vendor name might be at the top, middle, or even sideways. Total amounts can appear anywhere, mixed with subtotals, tags, and tips. And then third, resource intensity. Existing end-to-end deep learning solutions like Donut require massive data sets, tens of thousands of images, and heavy computational resources that aren't practical for most applications. This motivated me to develop a hybrid approach that balances an accuracy with efficiency. Here is my first approach: adaptive preprocessing based on image quality. Instead of applying the same enhancements to every receipt, I first analyze the image standard deviation, which measures contrast, and classify it into one of three categories. Path A handles faint receipts with low contrast, where standard deviation is below 30. These represent 29% of our training set. They get gentle contrast enhancement to recover faded ink without amplifying noise. Path B is a normal quality receipts, making up to 60% of the data, um, with standard deviation between 30 and 55. These get moderate denoising with a medium contrast enhancement. Path C handles shadowed images with high contrast, standard deviation above 55%, representing 11% of total receipts. These get aggressive adaptive thresholding to binarize the image and isolate text from dark backgrounds. The key insight here is that treating all images the same leads to data loss. Applying aggressive preprocessing to faint images destroys information, while gentle processing leaves shadows unaddressed. This adaptive strategy allows each image to receive exactly the enhancement it needs. Here is the complete hybrid detection recognition pipeline. It starts with an input receipt image, which flows to YOLO V8 Nano, our object detection model, running at 1280 pixel resolution. This high resolution is critical for preserving small text features on receipts. YOLO detects where the vendor, date, and total fields are located. Then we crop those regions of interest. Next, we run Tesseract OCR to extract the actual text. Finally, regex validation checks that the extracted text matches the expected formats with fallback strategies if primary extraction fails. The two key specs here is I chose YOLO V8 Nano for its lightweight architecture, only 3 million parameters, making it suitable for production deployment. And critically, I selected Tesseract over EasyOCR because Tesseract process images in about 0.8 seconds versus 3 seconds with slightly improved accuracy. Okay, now for the results, let's start with YOLO localization performance on our validation set of 344 images. Vendor detection achieved excellent performance at 96.2 mean average precision. This makes sense because vendor names are typically large, bold text consistently positioned at top of the receipts, making them easy target for a detector. Date and total fields showed moderate performance around 70 to 75%. These are more challenging because they are smaller text regions that can appear in variable positions. Dates might near the header or footer. The totals get mixed with subtotals and tax amounts. Overall, the model achieved 81% mean average precision at zero point 0.5 IUE threshold. This is quite a strong performance for document parsing, especially on a challenging datasets like SROIE with slightly variable receipt formats. On the right, you can see an example of successful detection with clean bounding boxes, accurately capturing the vendor name in the header, the date below it, and the total amount at the bottom. The boxes show high confidence, which is what we need for reliable downstream OCR. Now let's look at the end-to-end extraction accuracy, the complete pipeline from raw receipt image to extracted structured data. This table compares three approaches on our test set of 347 receipts. First, EasyOCR only as a baseline achieved 39% average accuracy. Second, Tesseract only achieved 40.2%, and third, our hybrid YOLO and Tesseract system reached 65.32% average accuracy. That's 25.1% point improvement over the baseline, or about 64% relative improvement, which is substantial. Let me break this down by field. Vendor extraction improved 36.3% points from 39.5% to 75.79%. This massive gain comes from YOLO localization, eliminating background noise like logos and decorative text, giving OCR clean focus crops to work with. Date extraction improved by 29% points from 36.6% to 65.42%. Again, localization helps by filtering out false positives like expiration dates or item timestamps scattered throughout the receipts. Total extraction showed a smallest gain 7.8% points from 47% to 54.76%. This is interesting and important. While we still improved, the smaller gain tells us something. The challenge for total extraction isn't primarily visual, it's semantic. Here is what I mean. Receipts typically show 5 or more monetary values in a vertical list: subtotal, tax, service charge, tip, and grand total. Our current regex logic sometimes picks the wrong candidate because it doesn't understand the meaning or spatial relationships between these values. This isn't limitation of OCR accuracy, it's reasoning problem. Looking at the overall gap, we detect fields 80% accuracy but extract at 65%. That's 15% point drop. This detection to extraction loss represents failures in OCR character recognition and logical parsing, not in finding the fields. This insight guides our future work toward learned extraction models rather than just better OCR engines. Okay, let me break down the remaining challenges and our path forward. First, regex brittleness. Our current system uses hand-coded pattern matching rules like looking for the word total followed by a dollar sign and numbers. While effective for standard formats, these hard-coded rules fail on novel layouts. If a receipt says amount due instead of total or uses unconventional spacing, our patterns break. Second, a semantic ambiguity. This is our biggest bottleneck. The question mark here represents the confusion between subtotal and grand total. When five monetary values appear vertically on a receipt, simple string matching can reliably identify which is the final amount to pay. This requires understanding the context and spatial relationship. The feature solution addresses both challenges, replace regex with named entity recognition, specifically fine tuning BERT on receipt text to learn flexible extraction patterns, and develop graph neural networks to model the two-dimensional spatial relationship between two text fields. For example, graph neural networks could learn rules like tax usually appears directly above the total or bottommost label amount is typically the grand total. These learned approaches would provide the contextual reasoning for our current system lacks. To conclude, this project demonstrates four key contributions. First, adaptive preprocessing solves image quality variance. By classifying receipts into faint, normal, and shadowed categories, we apply targeted enhancement strategies that preserve information rather than destroying it. Second, high resolution YOLO is viable for document parsing. At 1280 pixel input resolution, we preserve small text features while maintaining reasonable speed, achieving 80% detection accuracy. Third, the system is efficient. Processing receipt in approximately 1.5 seconds each makes this production ready for real time applications, not just research experiments. And fourth, the architecture is modular and scalable. We can independently optimize or swap components, upgrading to EasyOCR, using a different detection model, or improving the extraction logic without retaining the entire system. The result validated this approach: 80% detection accuracy, 65% end to end extraction, and a 25% point improvement over OCR only baselines. The system is ready for deployment in expense automation and digital archiving applications. Quick note on teamwork. This was an individual project where I handled all aspects from problem formulation, dataset preparation through model development, evaluation, and this final presentation. I'm proud of the comprehensive system we built. Thank you for your attention. Have a nice day.